So recently I've been exploring cheap power supplies on Aliexpress, and in my wanderings I came across this. It's advertised as an 1800 watt DC to DC boost converter, and it looks super beefy. It's got this giant toroidal inductor on top, it's got a massive heatsink, it's even got a fan. So this should be able to handle a lot more current, a lot more wattage. 1800 watts doesn't seem out of the question for this module. So we're going to put this thing through its paces and see if it holds up to its Aliexpress claims. And about the only way I have to take this thing close to 1800 watts is with this insane setup. I've got four 12 volt 350 watt Meanwell power supplies and two water heater heating elements that we're going to immerse in this vat of water. If I learned one thing in my physics class, you don't mix water with electricity. Here they are. The cheaper ones will not have a fan on the bottom. If you know you're not going to use it in heavy loading, don't get the one with the fan. They range in price pretty wildly. So 18 bucks, 15 bucks, 23 bucks, 13. But yeah, just hundreds and hundreds of providers of these. So this one has different versions of it. It says 1800 watts, 40 amps. Yeah, I think that's 40 amps on the input. So I found this little manual online, and I'm not even sure if this company still sells this. I can't find this product on their website, but this PDF is out there and it appears to be accurate, and it's a little bit more complete than what you can see. Obviously, a lot of the same information is getting cut and pasted between the various Aliexpress listings. So high power, non-isolated, so it's not isolated. Temperature controlled fan, CCCV LED, undervoltage LED, rated input current 40 amps, fused at 60 amps. That's right. 3 20 amp fuses, output 13 to 95 volts DC. Output power can be up to 1800 watts when input voltage is greater than 48 volts. Yes, I think that's right, because otherwise your input amps would have to be too high. So the temperature controlled fan provides a balance between noise and heat dissipation. Its design has a conversion efficiency of up to 98.1%. The undervoltage protection is adjustable, which can effectively protect various batteries and can also be used for solar cells. Constant current function can be used for battery car boost, battery charging, and so on. 320 amp input fuses in parallel protect against the risk of an unexpected short on the output. And we have constant voltage regulation, constant current regulation, and undervoltage protection on the input undervoltage protection regulation. The QS484 884CCCV 1800 watts is designed for lead-acid batteries, lithium batteries, solar cells, or power supply boosting for electric vehicle boost and battery charging. It is very powerful. For example, the original battery of the electric vehicle is 48 volts, which can be boosted to 60 volts to supply electric vehicles, which can improve the speed and acceleration of the electric vehicle. I don't know maybe we're talking about kids' toys, even a golf cart. Golf carts can run 100 to 120 amps through them. You try and run a golf cart through this, you're going to blow it to pieces. Maybe it's for kids' toys. Charging your electric bicycle, yes, you can do that. You can charge the original battery after boosting this boost power supply. So I guess what it's saying is that you can use, if you have a known lower voltage battery, say a 12 volt lead acid battery or something like that, and you want to charge your lithium ion battery and say it takes 40 volts, you can use this to boost it up. The battery voltage can be increased to make the electric car run faster, and the built-in instrument should not exceed 10 volts. I don't know that you're going to make an electric car run faster with this tiny little thing. Solar panel boost regulators. So yes, you can use this to maybe charge a battery from a solar panel. I've not used solar panels. Anybody out there watching this wants to chime in the comments how that undervoltage protection might help with the solar panel, that'd be great to hear. So we have a nice diagram here. So we've got the input fuses, the input plus and minus are nicely labeled, the output plus and minus are nicely labeled. We have our output LED, CV, output voltage adjustment, so that's our constant voltage. So there, you turn it clockwise to increase the voltage, counterclockwise to decrease it. The CC, output current adjustment, again, you turn it clockwise to increase the current limit and counterclockwise to decrease or lower the current limit. And then we have the overcurrent LED, the undervoltage LED, and the undervoltage adjustment. Efficiency versus output current. Efficiency seems to peak at around 5 amps output. And they got it above 94% the entire way. I'm not sure how realistic that is. And for voltage regulation, it says just connect a voltmeter to the outputs and adjust the output voltage until you get it. Current regulation, this is a little trickier. I have a load, so the load will tell me the voltage and the amps, so I can use my load to adjust the current cutoff that way. But you could also use the ammeter on your voltmeter to do this adjustment. Then it also walks you through doing the low battery UV protection adjustment. Precautions, it says the output positive and negative poles cannot be reversed and cannot be short-circuited. Obviously there's some fuses on the input, so if downstream something shorts out and draws a lot of current, those fuses should protect your source at least. If used for electric vehicle boost drive power supply, the input voltage must be 24 volts or more. The electric vehicle power is less than 500 watts yet, so I don't know. I mean, 500 watts is like a bicycle motor. I'm not sure what sort of vehicle they're talking about. Maybe they're talking about scooters or something like that. Pay attention to ventilation and heat dissipation when working for a long time. High current, high power, and full load in order to extend the service life of the power supply. And it says do not work at full load for a long time. Please use a 20% margin. Yes, I think 1800 watts on this thing would be just bananas. I wouldn't get anywhere near it for any long period of time. We have got the Aliexpress El Cheapo 1800 watt 40 amp DC to DC boost converter on the bench. I've got it wired up to a 300 watt bench power supply and my brand new Rigel 200 watt electronic load. We've got this supplying about 12 volts input and the output is adjusted to about 16 volts. We're going to test out some of the claims that you can find on the Aliexpress pages. Static operating current, 15 milliamps. So we can test that right now, right? This load is off, so let's just turn on the bench power supply and see how much current this thing is drawing. So it says it's drawing about 30 milliamps. So that's about twice what it says the static operating current is, so you know, whatever, it's close enough. Output voltage is 12 to 90 volts, continuously adjustable. Maximum output current is 20 amps, and it says over 15 amps, please strengthen the cooling. Well, we got a lot of good cooling here. I would have a hard time getting this thing up to 20 amps. So that's where it gets the 1800 watts, right? It says 90 volts at 20 amps. That would be 1800 watts. It's tough getting a load to handle that much current. We are going to play around with this little beastie. This is an 8.7 ohm resistive heating element meant to go into a water heater, an electric water heater. So this will take quite a lot of current. You know, its current is limited by its ohm rating. So at 90 volts, the maximum output voltage of this supply, we're going to get about 10.3 amps going through this for about 1,000 watts. So that's about the max I think, at least theoretically, I'm going to be able to hit with the equipment that I have. First, let's just test that it works. We have 12 volts coming in, we've got it set for 16 volts coming out, and we've got a very light load of 100 milliamps. Let's see what it does. Great, we're putting 2 watts through here. Awesome, wonderful. Let's go to 1 amp. So we got 12 volts in, 16 volts out, 1 amp output, 1.4 amps input, right? So that's about 92% efficient. So that makes sense. I think in these lower voltages, they're not terribly efficient. It's what you'd expect, and it's similar to what I've seen with other power supply, El Cheapo power supplies like this. So now what we want to do is let's test the under voltage protection. So this knob, what it's designed to do is if you're using a battery as an input, you can put a cutoff voltage, so below which it won't draw any current. So we got 1 amp current going right now, and let's go ahead and turn this counterclockwise, and it should lower the under voltage cutoff. And at some point we should get below 12 volts and it should shut down. Let's turn it clockwise and see if that is what it does. Maybe it goes down. Well, the under voltage, did the under voltage light go? Yeah. Under voltage protection light just came on, but it didn't shut off. It's still drawing an amp. It says low voltage UV protection adjustment. Low battery protection mainly prevents over discharge of the battery when the input voltage is so low that it can damage the power module and or the battery. Counterclockwise protection voltage is turned down until the UVLO LED is on. At this time, the power module does not boost. The output voltage will track equal the input voltage. Only when the input voltage is higher, the input supply will resume boosting. So that's what we're seeing. I'm not sure that's great protection. I mean, we're still drawing an amp, we're just not boosting anymore. Maybe the lack of a boost would cause your battery to stop charging. It's doing what's advertised. I'm just not sure how that protects a battery all that well. Let's test the lowest voltage on the input. The datasheet claims 10 volts is about the lowest it'll go. 9 volts, 8.5, so 7.5, we're okay. It's still boosting. If we go down to 7.4, there, you can see it fails to boost. 7.4 is the lowest input voltage you can have. And then what does it say? It says it's 10 to 60 volts DC input and 13 to 95 volts DC output. Let's go VSET, let's put it up to 10 here. Yeah, it looks like 10.7 is the minimum output voltage we're gonna get here. And let's see what our maximum boost is. Okay, now we're gonna go. Okay, so we're at about 48 volts, still 1 amp, so now we got 48 watts. Let's set our input voltage. The fans are starting to spin up. Okay, we're at 71 volts, 72 volts, something like that. 80 volts, 1 amp. Let's go for the max, oops. Okay, so 92.9, so roughly 93 volts, so a little bit higher than what they were saying. So we got 100 watts input and 92.9 watts output. Don't really need to do the math there, that's about 93% efficiency. This is with 1 amp out. We're going to put that to 2 amps. So that's 186 watts. There. So we got about 250 watts out and 264 watts in. Quite a bit more efficient. That's about 95% efficiency. That's because we're using a higher input voltage. It says the input voltage can go up to 60. So let's try that out. So we're at 60. So we're at 260 watts in and 250 out. Now that gives us 96% efficiency. So it's really pretty efficient. And the fan has not turned on. And this thing is not particularly hot. Yeah, I mean, it's not that bad at all. The maximum hot spot on there is 38 degrees Celsius. So we're putting 250 watts through it. The fan isn't even turning on. So that just speaks to the huge size of this heat sink. Okay, so let's now actually try the current limit here. It is better when we're trying to test the constant current mode on the DC to DC boost converter that we have this guy in constant resistance mode. So we're going to set up a nice constant resistance. There we go. So let's do, I don't know, let's make it 50 ohms and turn that on and see if it kills anything. That's good. Yeah, so we've got roughly 2 amps coming out right now. So now I'm going to spin this outwards and it should decrease the current limit. There we go. So you can see the voltage went down and the current limit went to whatever the current limit I'm setting with this potentiometer is. So obviously I'm at about 1.6 amps. If I turn it down further, I can target 1.5 amps. So now we're increasing the current limit. And if we keep going, we're going to go back up to the target voltage. Once we hit the target voltage, we're in constant voltage mode. So you can see the amperage is holding steady. So now we're going to decrease that current limit. Great. And it lowers the voltage. It manages the voltage to hit the amp target based on the amount of current the load is trying to present. So the fact that it's trying to be a 50 ohm load. Let's see how low we can go here. 1.1 amps. It says 800 milliamps is the lowest limit you can set. Yeah, I'm hearing a click, so 1.1 amps appears to be the lowest limit, so that seems to be incorrect. The circuitry here might be like plus or minus 20%. Let's try and get this up to the max that I can do here on the bench top with the power supplies I have here. Let's set our, well, I'm going to do a max 60 voltage because that's going to give us the highest amperage range. Okay, so now we're at 172 watts, and we're just going to lower the resistance until we get kind of a maximum here. So it's our maximum current here. So this is 5 amps. This is what it says that it can do on that side. So we're going to watch the upper power supply, and once we get up towards 5, we're going to be like, okay. Oh no, wait a minute, I need to go down on the, it's probably going to be hard to see. So we're at 37 ohms, 250, 240 roughly, 35 ohms. Okay, I think that's about all we're going to get. So this is 300 watts up here, which is the limit. And we're at 5 amps at 60 volts output. That's 96% efficient. So it seems to get more efficient the higher the load you're putting on it. You know, the max is about 40 degrees Celsius, and it's still that switching chip. And that toroid looks super hot, but it's only 38. The switching chip is hotter at 41. That's fascinating. Okay, so we have roughly 50 volts here, and we're going to see if we could get some higher amps. So we're just going to go down. Okay, it looks like that's the best I'm going to do. Input terminal is now, something around the input terminal is now the hottest at 50 degrees Celsius, although it's still, the fan is still not on. Toroidal inductor is still not terribly hot, although it looks hot. It's just not the hottest. The input terminals. And that input terminals are because we are getting some pretty high amperage here. So we got about 10 amps in. So that's going to cause some heating. You can see the wires are getting a little bit warmer. They're not terribly. How hot is that? So another thing that I wanted to test was the output switching noise. So we have got our spring lead on this so we don't get a giant loop with the ground lead, and we're just going to connect it across the terminals here. See what we get. Boy, big sparks, that's fun. Holy crap, we're getting 8 volts peak to peak. That's with the bandwidth limit off. So let's put in the bandwidth limit. Okay, that's a little bit better, but we're getting 5 volts peak to peak. That's not great. And that's right at the terminals. And I have tried this across one of the output capacitors as well. It doesn't change things. So if anybody in the comments wants to say, no, you got to go straight to the output capacitor, no. This is just inherent in the design. This is one of the larger amounts that I've seen. I'm wondering if I decrease the boost by increasing the input here. So let's bring him up to like 48 volts. So now our boost here is tiny. And you can see on the output, our voltage peak to peak did go down quite a lot. So we got the 20 megahertz bandwidth limit. We turn that off, we go to 7 volts peak to peak. Jeez. Okay. And let's look at the period of this noise. Right there. Yeah, so that switching noise seems to be about 105 kilohertz. So I call that like 100 kilohertz. Not nice stuff. And we got 3.5 volts peak to peak here. So these are big, messy supplies, and you can kind of see the ringing here. This is why this is cheap. If your load can stomach this sort of thing, if it's just a big dumb battery, I don't think this is terribly harmful to batteries. Lithium-ion batteries are particularly sensitive to being overvolted, although this is, just a very, very quick overvolt, and I doubt a battery is going to be able to respond to that quickly enough. Let's see if we decrease the amperage if things get better. So we're going to up the resistance, 1.7 amps, and now we're down to 2.3 volts peak to peak, roughly 1 amp, and we're down to 2 volts peak to peak. So the higher the boost, the more switching noise we have, and also the higher the amperage, the more switching noise we have. We have the guy under the microscope, and we're zooming in here on the main 16-pin chip, which is most likely the controller here. It is a TL494C, which is a Texas Instruments PWM controller. So let's take a look at that real quick. TL494. So here's the data sheet for it. Complete PWM power control circuitry, and it says application, desktop PCs, microwave ovens, servo PSUs, so, power supplies basically. So totally just a, multi-purpose. Basically, it's used to control the MOSFET. It's used to control the switching circuits, which drive the boost converter. Yeah, oscillating frequency, 1 to 300 kilohertz. I think I saw in some of this stuff it was 150 kilohertz. We measured about 100 kilohertz, 110 kilohertz, something like that. This is not a high frequency controller. Yeah, I don't think there's much else to look at here. This is probably most assuredly some form of a clone. That looks like LM358. Yeah, it's a dual operational amplifier. So it's probably used for the constant current potentiometer and the undervolt protection potentiometer to compare those. So they have like little resistor networks that work in concert with the potentiometer, and it's used to compare to a reference voltage to decide whether or not, where you are in that particular setting. There's no other real logic in here. And I think this is one of the reasons why, there's no battery protection on here. Like if you're going to charge a battery, there's no battery protection on here whatsoever. Also, the undervolt protection has a weird, kind of weird behavior where if the input source is undervolt, it just outputs the same voltage as is input. It doesn't shut anything down. Well, it just doesn't have the circuitry to do that, right? Basically, this is just a boost converter. A boost converter can do a couple different things. It can operate from 0 boost up to a maximum boost, and that's it. So they kind of had to choose the behavior that they wanted for undervolt protection, and they chose, 0 boost is the best we can do. We can't shut down the output. We can't shut down the input. There's nothing on here to gate the output or the input. None of the sorts of beefy kind of hardware that you need to be able to do that. Let's see, there's one other little guy here. XL7005A. So there's a little buck converter in here that's probably using the input voltage to provide the operating voltage for all the internal circuitry. So yeah, it's dead simple. There's really not a lot here other than, these giant MOSFETs on the back, which just, aren't all that interesting. I mean, imagine, could I bend one up? That's a MOSFET for the DC to DC buck converter that supplies the, kind of logic voltage. Here we have the NTC, so there he is right there. So that's just measuring the temperature of the heat sink, and it's got some thermal compound surrounding it. So that's what turns on the fan, using the little fan port here. And here we have the 3 20 amp input fuses, so there's a total, they're in parallel, so there's 60 amps of input. I think the max rated, they say, is about 40 amps of input. I would say that that's optimistic. Like, I saw this thing getting super, super hot around 30 or 35 amps. So I think, I don't know, maybe you should pull out one of these fuses. Or maybe 2. Yeah. 470 microfarad, 63 volt capacitors on the input, and 470 microfarad 100 volt capacitors on the output. Now, the output goes up to 93 volts, and the input, according to the various sources that I saw, can go up to 60 volts. So you're really close to the maximum capacity of those capacitors. My version, so one of the versions that I have has this written on it. Another version that is virtually identical, like, you know, part by part, almost identical, does not have this kind of model number on it. So let's take a look at that model number. You get a lot of Aliexpress listings. Yeah, this one's pretty good. It even has like a little schematic here. That's similar to the noise that we saw on the output. This is cool. No, this is very similar. Solar pin mode, voltage regulation. Yeah, similar. Why not? Come on. Let's bend her up and see what happens. Just do it very slowly. Okay, so that's the MOSFET. This is IRFP4468. Strong power MOSFET, 100 volts. So that matches, so it's not under spec there. That's good. So they can say high efficiency synchronous rectification in switch mode power supplies, uninterruptible power supply, high speed power switching, 175 C operating temperature, hard switched and high frequency circuits. Okay, so it says continuous drain current, 195 amps max. So, I mean, it seems like even the lowest max here is 25 amps, and our rating is 20 amps output. What this one's going to do. Put a little alcohol on there. 100 volt power Schottky rectifier. Nice. High junction temperature capability, low leakage current, low thermal resistance, higher frequency operation. This dual diode, common cathode, Schottky rectifier is suitable for high frequency switch mode power supplies. Yeah. And I'm going to assume the other three are the same, or the other one. I think this one's going to be a MOSFET. I don't think that's going to be a diode. That's going to be a MOSFET for the buck converter. IRFB3206. This is for the buck converter that takes the input voltage up to 60 volts, and it's good. It's rated for 60 volts, and steps it down to logic level voltage for the control chip. And I didn't break any of those pins. Yay, let's put it all back together. Lots of good thermal vias here. I think you can kind of see why this was heated. This is where the power comes in. This sort of setup I just don't think it's not sufficient for the 30 to 40 amps that you're going to be inputting if you're driving high current on the output. There are some warnings that say if you're going to be outputting 1800 watts, don't be inputting anything below 48 volts. That's because of amps. So if you're at 20 amps on the output side at 1800 watts, doing 90 volts output, you're going to be close to 40 amps on the input at 48 volts, like half of the output voltage. So this sort of setup here is not designed for high amperage input. I don't even know what this connector is. What is it? Let's see if we can find what this connector. It says it's a 30 amp connector, so 300 volt 30 amp connector. We had it above 30 amps. I'm almost certain of that. And in use cases that this power supply will allow, you can go above 30 amps. So, you know, buyer beware. Be careful with this thing. Definitely, if you're going to be running higher output, make sure that your input voltage is high enough that you can get the amps below 30. Okay, so I have got my 2 electric water heater immersion elements suspended in a pool here, and I'll show you that later. Actually, I'll show you that on screen right now. And we have got a measurement of the voltage out of the power supply, and the voltage in is 48 volts. These are 4 Meanwell power supplies. They're isolated, which means that their individual output grounds are not tied to the earth or the input ground, so you can chain them together. So the only problem is that you increase your voltage, you multiply your voltage by 4, but you don't multiply the amperage by 4. If each one of these power supplies can only handle 30 amps, altogether they can only handle 30 amps in series like this. With this setup, I'll be able to do 48 volts at roughly 30 amps. So, do the math on that. That should be around 1400 watts of output and into my two loads. So these are two 8.7 ohm resistive heating elements. I can put them in parallel to get them to take about twice as many watts. So right now, I've got only one of them hooked up, and I have current limited this all the way down to its very minimum. If I turn this thing on with the current limit off, the Meanwell power supply is just shut down. You've got to slowly ramp the load on. And even so, when I do this, it starts out at a relatively high load. So I've got a little current clamp here, and this is measuring about 6 volts. So if we look on here, it says that 20 amp output, I get 100 millivolts per amp. So that means I need to multiply this by 10. About 6 amps into my one resistive heating element. The other one is unconnected. This ground is loose here. I'm just going to be very careful around that. I do not connect any of this stuff live. This is just like, I try and keep my hands away from it. This is, I want to say out loud, this is super unsafe. Don't do this at home, folks, unless you're an expert. And I'm not an expert. I haven't electrocuted myself yet, although this might be found footage. Who knows? Anyway, and this is showing the output voltage. So we have 48 volts in always, remember that, and we're getting 47 volts out. So basically we have 0 boost right now. But now what we're going to do is we're going to dial this up with one load here and see how high we can get with this 8.7 ohm resistance. If we do the math, I'll do the math on screen and make a prediction about where we should be able to get there. And let's see what we get. So this current clamp, I can move it around. I'll have it on the output, so this will tell how much current the load is sinking. And then as we move the current limit, we're going to see, make sure I don't obscure anything here. So as I change this, you should see the amperage go up, and you should see the voltage go up as well. There we go. So the voltage is going up, the amps are going up as well. And we're at 48 volts in, so now we're starting to boost more and more as we remove this current limit. Okay, so 10 amps. And I don't know if you can hear those Meanwell power supplies, but they're really humming now. We have 11 amps, and we're almost at the max boost voltage where those power supplies are singing. Okay, that's it. So we got 93 volts on the output. We've got 11.6 amps on the input. And we can do the math on that. 93 times 11.6. We are well over 1,000 watts. And let's look at the input amps here. So we're at 23 amps on the input. We're not going to be able to get much higher than that. These are rated at 29 amps. So we're going to have to play it by ear. I think as I try and ramp this thing up to its maximum, I'm going to watch the input amperage most of all and then measure the output amperage. But I want to keep these below their rated maximum because, I don't want to release the magic smoke. The power supply's fan has now come on because we're getting pretty toasty. So our max is 67 degrees Celsius. That's not, that's toasty. The Meanwell power supply fans have now come on as well. And we can see the leads coming in are getting a little toasty. Those leads are about 40 degrees or 30 degrees Celsius. So the input leads are, they're getting warm to the touch. They're not hot. The power supplies, all their fans have now come on. Okay, now let's hook up our second load in parallel, and we're going to turn everything off. I'm sad I didn't get it on video, although it probably makes me look stupid, as I tried to connect this with it live. I got a really big spark and did a little bit of welding. So now we have these two in parallel. So basically each one of them has their own independent connection to the load. I'm going to put the current meter on the input just to make sure that we're protecting those power supplies. Okay, so we got 11 amps input, 46 volts output. So we're good for now. Okay, so now we're starting to go up. So we're at 50 volts, 13 amps on the input. So we're just watching the input here this time around so that we protect those power supplies, because these two loads can definitely pull enough to burn out those power supplies. And I'm not sure what'll stop them. 17 amps. I think our previous max was 23, and it looks like we'll hit that easily. So let's get up to 23. Okay, so we have 23 amps input. Now our voltage is only 65 volts output. So you can see those loads are actually quite thirsty. And now this is interesting. We'll have two different amperages, and I wonder how balanced they'll be. So that's about 8 amps out on one and about 8 on the other. So they are pretty balanced. That's nice. I'm glad to see those being balanced. And then I think if I put the clamp around both of them, do I have to go up? No. Is he going the... Oh, he's going the opposite direction. Well, that was fun. Did you see that? So this is physics. One is going one way, one is going the other way. They can't, their magnetic fields cancel out. So if I want to go around both of them, I have to go the right direction. Make sure I don't electrocute myself over here. And now I get the 16 amps total out. So now we're doing some pretty good amperage through this guy, but we're at a lower voltage, right? Okay, so we got 24 amps on the input, 25, 26. Seem to have leveled out. 27 amps. I don't know if these guys are limiting. They are getting toasty. Oh, this says we're current limiting here. I'm not sure what that means. That must mean we're at our max current limit here. So we have 17 amps on the output and 70 volts output. 17 amps total, 8 on one, so that's roughly 50-50. So that's roughly 1200 watts. And I think that's it. Like, we can't do any more with these power supplies. Like, it's 48 volts. This is as high as we're going to get on the output. Any more than that, this thing's output current protection comes on. I'm guessing it would probably have a lower level if we had a higher input voltage. So if we were able to get the input voltage above 48 volts, so if I threw in a couple more Meanwell power supplies, we would probably be able to get above 1200 watts. But you can see how hard it is to get to 1200 watts here. Meanwell power supplies over there are getting toasty. They also smell atrocious. I don't know what's going on. I'm not sure. I don't think I'm damaging them. I mean, they're below their rated capacity. That's 26.9 volts, so 27 amps in. Let me look at the input leads here. Input leads are 43 degrees Celsius. It's getting warm. I mean, they're not melty. I mean, I wouldn't recommend this sort of cabling for any sort of permanent installation, but you know, for a test setup, this is cool. Our water here is getting nice and toasty. It says it's at 45 degrees Celsius. So I think that's it. I think that's all we're going to be able to do with our 48 volts input. You know, we were able to get 1200 watts output. That's the best we're going to be able to do because we need a lower boost to get a higher current output. I mean, we're 2/3 of the way there, right? You know, so that's good. But yes, I would need more power supplies to get to a higher input voltage. I wanted to show you the situation here. So this water is, it's pretty warm. So those heating elements did their job. They kept their cool. They dispersed a lot of power. So that's a way to make a poor man's not an electronic load. This is an analog load. Each one of those is 8.7 ohms, so whatever voltage you put through them, there's very simple math to tell you how much power they'll consume. They are designed for a North American 110 volts, so we got close to that. They're designed for AC voltage, but they're just dumb resistors, so they don't care. DC voltage works just great. I would not do these in the open air. They will melt down. What's the verdict on this cheap little pint-sized power supply? It's caveat emptor. This thing can output pretty significant wattage. This thing is certainly much, much more capable than this tiny little $5 power supply. This is kind of a joke. You're going to be able to charge small batteries with this. With this, I think you could charge bike batteries. You could charge batteries from batteries. The constant current mode works. The constant voltage mode works. And the under voltage protection works for some definition of works. And we were able to get this up to about 1,000 to 1,100 volts of output. I can only provide this thing with about 1,400 watts of 48 volt input. You're not going to get anywhere near the 1,800 watts output with lower voltages. Really, you're limited by the amps on the input. If you want to get 1,800 watts output, you probably need to input something like 60 or 70 watts on the input so that you can get your amps low enough that you're not going to burn up the input terminals. I'm not sure what use that is. I don't know who has a use case where they're stepping 75 volts up to 90 volts at 1,800 watts. If you have that use case, this will probably do it and probably won't burn up doing it. I did see that in the use cases where this little thing was screaming and burning up, this thing's fan didn't even turn on. So for anything that you might have thought to use this for, I would pay 2 to 3 times as much and get this. It's got the thermal mass. I mean, these heat sinks are a joke. Those switching MOSFETs and the diodes are definitely much inferior to what we found on this board. So this is kind of a little bit of a joke, and you can find this for, $10 to $15 on Aliexpress, whereas this was like $3 to $5. Everything is beefier about this and designed much, much better and designed to handle much higher amperage and so forth. It's even got fuses here. Like, they actually thought about fuses, whereas here, like, you're kind of on your own. The fan actually does work. We had to get up around 800 watts of output before the fan started turning on. I like this for, kind of ad hoc bench power supply, like if I need multiple sources of voltage and I don't care much about the quality. That's the other thing, the quality of the power that's coming out of it. We found similar poor quality, lots of switching noise on the output, lots of switching noise in the output on this one as well. So similar levels, like multiple volts peak to peak on the output. I think in general, batteries tend not to care all that much about dirty power. I would be a little worried with lithium-ion batteries because they do have very strict voltage limits. I don't think a spike, microsecond spike of voltage is going to harm the battery. Like, it's not going to, the batteries don't respond quickly enough to that electrochemically to really damage them. But it would be a concern. Like, I think if you're charging batteries, there's a reason that a large 48 volt battery charger costs $100 plus. There's a lot of protection and extra circuitry in a actual professional battery charger that's just missing here. This is the minimum that you need to do to get the job done. And they've done it. And it's adjustable, which is cool. Like, a lot of battery chargers are not going to be adjustable. This is nice. If you've got different size battery packs, you can switch it up. Although you're going to have to be careful, right? Don't leave it set for your 48 volt battery pack, and when you go over to a 36 volt or something like that, don't do that. So I think it's a worthwhile little power supply if you understand its limitations. The 1,800 watts is Aliexpress magic, totally based on the absolute best case scenario usage. And any real world scenario that you use this for, I would say 500 to 1,000 watts is probably about the max that you can expect out of this. If anybody else takes this up to 1,800 watts on a regular basis, this particular module, let me know in the comments. I'd love to know how you're using it and how you're getting that level of performance out of it. Thank you for watching to the end. I'm Josh, and this is Signal Drift.